Hello, thanks for coming. The reason for giving a talk on the history of robots is twofold. One is that it's an interesting topic, and the second one is that we learn from history, as George Santayana pointed out in 1905. It's a good thing to learn from history. Typically, when you ask people, what is a robot, please define it, the typical image that comes to mind is that of a metal monster that may or may not be computer controlled, but it certainly is out of control and very dangerous. That, however, is not a definition that stands up to closer scrutiny. So I'll deal with all the definitions that I've ever seen of the attributes of robots. And that is, well, there's so many attributes. And they're self-contradictory. Some say it's got to be useful, some say it's got to be intelligent, others say it's indefinitely stupid. The one common denominator is that in all of these descriptions, a robot is something that is surprisingly animate. So for the purpose of most of this talk, I'll stick with the definition that a robot is something that's surprisingly animate. The question, of course, is then what is the meaning of the word surprising? Because if you had a washing machine, if you could take it back to the Middle Ages, I guarantee you that people would have been astonished by this surprisingly animate behavior of this machine that could somehow supplant the labor of people beating clothes in the river with rocks. Doing it a different way, perhaps, but nevertheless, it's not surprising at all anymore, and we don't consider it a robot, but back then it would have been considered that. Now, the word robot actually came into English primarily as a result of a play that was produced, play by Karel Čapek, a Czech author. In the Slavic languages, robot simply means work. Subsequently, it took on the connotation of drudgery when the Soviet Union in its early years created labor camps that were called robot camps, and the work was not very pleasant. But the word simply means work. The story is that Rossum has invented artificial protoplasm with which he can create artificial human beings very cheaply, I think about $25 a person. And at that price, all the nations of the world sign up to get robots in their armed forces. And once the robots are in control of the weapons, they exterminate all of humanity except for two people. And then the robots realize they can't self-replicate, so those two people turn into a new Adam and Eve, and the whole cycle can start over again. A very common theme. Notice, though, it's artificial protoplasm, not metal. Here's some other examples of robots not metal. The golem, created out of a lump of clay by Rabbi Ben Lo in the 15th century. It's definitely not metal. Frankenstein's monster, the story of Frankenstein is written by Mary Shelley. And Mary Shelley is actually the daughter of the poet Shelley, who was very good friends with Lord Byron. And I'll say a little bit more about Lord Byron later on in this. Now here is, in history, the first statue that could do the surprisingly animate thing of talking. This is a huge statue. You see right here, this actually is the size of a person. So this statue is about 80 feet high. And every morning as the sun came up and heated the statue, it emitted chirping noises. Presumably there were air pockets that heated up and the air came out and made the noises. Nobody knew what they meant, but fortunately there were priests who could interpret exactly what it meant. Of course, talking is no longer surprisingly animate. It was Thomas Edison in 1892 created a talking doll, and then more recently, Texas Instruments brought speaking into the range of toys. And now it's quite commonplace. Toys, well, dolls not only can speak, they can eat, they can wet, and so forth. Here is the mechanical man from Ozma of Oz, one of the Frank Baum stories. He can walk and talk depending on where you wind him up, but he cannot walk and talk at the same time, rather like a former president of the United States. Here's the first example of articulated arms. The arms can swing. They have 1 degree of freedom. By comparison, human arm has approximately 27 degrees of freedom. There isn't a robot on the market yet that has anything approaching 27 degrees of freedom, but think of all the degrees of freedom and what you can do with it that this kind of machine cannot do. European cathedral clocks are very common, but the very first one was started in Padua in 1344. The scene you're seeing here is one that's in Prague, though. It was first created around 1410, and then it was enhanced over the next 4 centuries. Typically in these cathedral clocks, there are figures that move around and that beat on drums, or that wave scepter, a king waving a scepter, rooster that crows, and so forth. Very surprisingly animate, and people get a lot of enjoyment out of it. Around 1650, mechanical paintings were very popular. So here's an example of a mechanical painting. Of course, the clock is moving, but in addition, the balloon is drifting back and forth, the windmill is turning, the train is running, boat is moving, and so forth. In its way, surprisingly animate. Really, the ancestor of this is the pendulum clock, which was invented by Galileo and then perfected by Huygens. And that dates back to a much earlier device, namely the clepsydra, from several hundred years before the Common Era. Now here's a wonderful machine around 1773 by Jacques-Droz, a mechanical designer. It's cam operated, and it had a repertory of about 8 things that it could write on a piece of paper. So think of it as a very sophisticated XY plotter, but it's more than that because the eyes blink, the head moves from side to side, the chest moves in and out. And of course, you can't see this in action, but there's a modern guy in Switzerland who makes copies of this. He makes them much better than the original. If you want to buy one, anybody have $100,000 to spend this way, here's a film of his device. You see the cams here moving, and now you can see the device as it draws. It's also playing music from a music box at the same time. Periodically, the pen will be dipped into an ink well, and you'll see in the next scene the eyes blinking and the head moving and the chest, the feet moving, the chest breathing in and out, and so forth. Highly realistic. Another machine built by Jacques-Droz is this piano player on the right. Now, again, they're cams that are hidden that are moving the piano player, and tendons are pulling the fingers, and the fingers are really playing on a small piano. So it's not a hidden music box. But in a way, the technology for this, you can start with cathedral carillons and then work to cylinder music boxes, and you get this. By comparison, the robot bear, which was installed in Disney World in 1955, it just appears to be playing a piano. There's really a hidden music box or recorder that's playing the music. So this is much less sophisticated than that. The player piano is also surprisingly animate. It was invented by Fourneau in 1863 and perfected by McTamaney. And while we're on the subject of music, back around the year 1728, the richest man in the world was arguably the Holy Roman Emperor Charles VI. If he wanted to listen to a concert, he would simply give a command and a performance would take place in the Vienna Music Hall. This picture was not made in 1728, by the way. By comparison, Sony Walkman is a robot orchestra. And of course, the Apple Pod is a slightly more recent version of the same concept. Now, in the entire history of robots, hi Les. In the entire history of robots, I consider this to be the most remarkable of all, Wilkinson's duck. It's shown here so you can see the cams and the covering is off it. But you have to imagine this covered over and the duck itself covered with feathers so it looks like a real duck. People would pay, they'd come into an audience, they'd sit down, they'd wait for the operator to start the show. The operator would turn it on, and the duck would look around the room, And then you could see from his expression as he stretched his neck in different directions, he was looking for food. So the operator would put a container with food in front of the duck, and almost immediately the duck would start dipping his beak in and swallowing the food very rapidly. And then you could see from the pained look on his face that he ate too fast and he had a stomach ache. And he looks more and more unpleasant as he flaps his wings. And finally, he gives a grunt and he relieves himself on the table, and a chemical smell spreads out through the room. And it's wild applause at the end of the show for Wilkinson's duck. Anyhow, another great machine was a fraudulent machine, von Kemplen's Turk. This is a machine that played reasonably good chess a long time ago, 1770. At the beginning of the show, an operator would open this compartment, and then he would light a candle and hold it behind the compartment so you could see that nobody was hiding behind the gears. Then he would put the candle down, blow it out. He would open this door also, and he'd open the drawer so you could see nobody was hiding anywhere else. And he would close all the compartments, and the machine would start to play. It played in many exhibitions. It occasionally lost, but very rarely. It played a celebrated exhibition against Napoleon in 1809. The final position shown here where Napoleon lost, and he was rather displeased at losing. So he tried to take back his move, and the machine, in anger, knocked all the pieces on the floor, making whirring and clicking noises as it did it. How it worked, of course, is that there really is a human hiding inside, and he's got a pantograph linkage here. He's also got a candle in the box, and there are magnets underneath the chess pieces and little springs that he can see which piece has moved where. And he sets up his own board inside, and he figures out, and he's a pretty good chess player, so he can usually win. He's initially hiding in this compartment. He waits until the back door is closed, and then he gets behind the gears. He's a bit of a contortionist and very small. How it worked was revealed for the first time in a magazine article, not in Europe, where this robot was on display, but actually in the United States by somebody who had never seen it in action. He reasoned out how it had to work. That person was Edgar Allan Poe in 1836. The first actual chess-playing machine of any sort was invented by a guy named Leonardo Torres y Quevedo, shown here, demonstrating the machine to von Neumann. It's a mechanical and electric machine, and all it can do is play king and rook against a king, which is a rather simple ending. He's a bit of an inventor. He also built some sort of cable car that goes over Niagara Falls, although I doubt it's still in operation. Again, coming back to the theme of surprisingly animate, calling something a brain certainly qualifies as being animate. And ENIAC, which was the first large-scale electronic computer, was generally characterized as being an electronic brain. And then some people would argue that the thing that really characterizes animals is their ability to respond to a changing environment, which is the concept of feedback. But the first illustration of feedback in engineering is the use of windmills that could automatically steer towards the wind. At least I believe that's the first. If anybody knows of anything earlier, please tell me. Now I'm going to get into robots in the context of artificial intelligence. And there sort of were four challenge areas that people identified. One was, could you make a robot that could play chess? Because that would demonstrate intelligence, which is surprisingly animate. Could you have robot vehicles that could demonstrate mobility, or vision systems that could do recognition, or arms that could do dexterous operations? With regard to chess, in 1968, John McCarthy and Marvin Minsky, the two people who coined the term artificial intelligence, they said that within 10 years, a robot would be chess champion of the world. A computer program would be chess champion of the world. And David Levy, who was a senior master in chess, he didn't believe them. And he said he was willing to bet 1,000 pounds that they were wrong. So each of them took on a bet of 1,000 pounds. And 10 years later, he won that bet. It didn't take 10 years. It took nearly 30 years until IBM Deep Blue beat Kasparov in 1997. Mobility. Here's the beast from Johns Hopkins. applied physics lab in 1972. This is a battery-powered vehicle that could roam under its own power around the applied physics lab. It had a sensor so it wouldn't fall down the stairs. If you left your office door open, it would probably come into your office, wouldn't do anything very intelligent. If the power got low, a tape recorder switched on, it said, I'm hungry, and it looked for a plug on the wall to plug itself in to recharge the batteries. There are some apocryphal stories about how it mistook somebody's leg for a plug once. The Stanford cart, 1972, the original goal, as Les Ernest will well remember, was to drive autonomously to San Francisco Airport, a distance of 23 miles. And here you see it navigating in the back of what was then the computer science lab, which is the power building up on Arastradero. It's now a horse farm. Again, a battery-powered vehicle, radio linked to a much larger computer. The first major element of progress was made when Hans Moravec did a PhD thesis where he got this to navigate around the parking lot, avoiding cardboard trees. And the average speed that he achieved in his PhD thesis was 23 miles per year. Now, of course, there's been a lot of progress since then, but I'll come to that later. And here's Shaky the robot from Stanford Research Institute, SRI, a project headed by Charlie Rosen, called Shaky because it would roll forward and then it would stop and sort of bounce for a while. Shaky was given a task of planning, which is a wonderful task involving intelligence. Here, Shaky has been asked to knock that block off the platform onto the floor, so Shaky has to first figure out where is the ramp, then push the ramp in place, then roll up the ramp, and then knock the block on the floor. So it's a sequence of planning steps, and the computer could do it. Hot cell teleoperators were invented around 1944, 1945, because people were starting to build nuclear weapons, and they needed to handle very radioactive materials like plutonium and fabricate things in a shop. And so the issue was that they couldn't actually be there. So they instituted these systems with a lead glass shielding window where the operator was on the outside, and whatever he did, the pantograph linkage mirrored it so that the same thing was happening on the inside. And a few years later, it was necessary to add force reflective servos because otherwise the operator didn't know how hard he was grasping anything. The word teleoperator has sort of gone out of vogue. Nowadays, people use drones as the word, even if it's not necessarily an air device. Now, here is the first computer-controlled mechanical hand. Heinrich Ernst did his thesis at MIT in 1961. With sensors in the fingers, the computer would tell this robot to grope around aimlessly, feeling to find blocks, and then when it found blocks, it would stack them up. Ernst was quite insistent. He said, children learn to function without any prior knowledge of trigonometry, kinematics, dynamics, or control theory, and therefore he absolutely refused to put trigonometric functions into his computer program. It was a matter of principle for him that he wanted to imitate what children were doing. Ernst, by the way, then got hired by IBM with the stipulation that he never work on robots again for the rest of his life. And then we skip up to 1974. At MIT, the state of the art had improved a lot. This was the copy demo where anybody could build any kind of tower out of 1-inch blocks, and the robot camera would look at it, and then the robot would build a replica of it. Or if you wished, it would build a mirror image replica of it. 1974, other things were happening, by the way. Victor Scheinman had designed the so-called Scheinman arm, and lots of universities were getting them. There's one, I think, that's on display here in the lobby. And in 1974, at the AI lab at Stanford, Lou Paul programmed it to solve the instant insanity puzzle, where each cube has combinations of colors, and the challenge is to stack them all up so that each column has all 4 different colors. But you can see that when the camera is looking at it, it might see only 2 faces at a time or 3 for maximum. So the first part of the program, the robot has to pick up blocks and turn them around so the camera gets to see all the faces. That takes about 5 minutes. It then solves the puzzle. That takes about 2 milliseconds. And then it stacks them up with the solution, and that takes another 5 minutes, and usually the stack doesn't fall down. In the process of doing this, they had to write a very general program, something that could take anything and turn it upside down. Absolutely anything, provided it's a 1-inch cube. And here's Freddie the robot in the University of Edinburgh. Donald Mickey wrote a program on a very large computer for its day. It's significantly smaller than my cell phone today, but this robot arm, which dangles down from the ceiling, is huge. And there's an XY table on the floor, which is again huge. And initially there are 7 pieces for this. There are 4 wheels, 2 axles, and a body in an aimless heap. And the camera looks at it, figures out what's what, palletizes it, and then over the course of the next 8 hours assembles this. This led to some criticism in England, and I'll talk about that criticism later on. Now we'll talk about useful robots, because none of these robots was useful. As Aristotle said a long time ago, when the loom spins by itself and the lyre plays by itself, then man's slavery will be at an end. So in 1974, the people at Stanford decided they would actually try to demonstrate something useful in a robot, and they demonstrated the water pump assembly, where the same Scheinman arm now picks up the water pump base, puts it into place, gets 2 locating pins from holders here, puts the pins in place, gets the gasket, puts that on, gets the top, puts that on, picks up the power tool, gets a screw from the screw feeder, runs in 1, 2, 3, 4 screws, puts down the power tool, returns the 2 locating pins to their holder, picks up the tool again, and gets the last 2 screws and runs them in. About 5 minutes for the operation, and I've been told it was about 30% reliable. But it is certainly the first demonstration the robot could do anything remotely useful. Shortly thereafter, a project was started at IBM. I was one of the people on that project, where we put together a robot we affectionately called Klutz. And the first thing I programmed it to do was to assemble the 16 pieces of the Mattel Build-A-Train. Within a year after that, other people were programming it to do something where it would pick up power tools and assemble what's called the rail support of an IBM Executive D typewriter. It was kind of impressive to watch it assemble 25 pieces from that typewriter. But there's a lesson in all this, and that is that this 1975 typewriter had 1,000 parts. By comparison, in 2005, I added up all the parts in a printer, typical HP printer. It was about 40 parts, and I think it's probably gone down since then. The point is that designing things for ease of assembly very often eliminates the need for robotics completely, because it gets so easy to assemble that people can do it very, very quickly. Assembling 1,000 parts was a big challenge. Assembling 40 parts or fewer is not much of a challenge anymore. I enjoyed writing a program. There was an infrared sensor, an emitter in one finger and a receptor in the other finger. So I wrote a program that simply waited forever, and if something went between it, it would try to grab it, which would make it the world's 2nd most expensive flycatcher. That, of course, leads to the natural question. What would be, in all history, the world's most expensive flycatcher? Does anybody know? Well, it's Barry Bonds. Anyhow, speaking of baseball, around 2005, there were some reports out of Japan that they had developed a robot batter that could hit a ball at 200 miles an hour, and a robot catcher that could also do that. I'm skeptical when I see balls on the floor here that clearly it's fouled off or missed completely. However, in 1981, Russell Anderson at University of Pennsylvania wrote a program that played a respectable game of miniature ping pong. Here's the robot holding a stick to which a paddle is attached, And the vision system is anticipating where the ball is going, and it's getting the paddle there to return it, although it's on a small table, not a real ping pong table. 1983, IBM came out with a product called the box frame robot. Believe it or not, that's me in the picture. I had a lot more hair then, and it was a different color. One of the things that we did in the early years was see if we could get it to pick up a raw egg, and it's astonishingly easy to get it to pick up a raw egg. And it's just, there's no challenge at all in that. Now, you may think that this is a strange product for IBM to be selling, and they only sold it for a few years before giving up on that field. But in fact, back in 1930, IBM was selling a precision cheese slicer, which is even more strange. By 1980, there were machines that were starting to do component insertion using robots. Here's a machine that I helped influence. Actually, prior to 1975, I think something like 99% of all card assembly was done by humans. And nowadays, probably 99% of all card assembly is done by machines. So there's a transition there, but I think I may have been the first person to demonstrate that a robot could actually accurately insert a component in a card. Of course, nowadays you don't insert components, they're flat packs mounted differently. When we were doing this, some people said, hey, wait a minute, robots are going to take away the jobs of a lot of people. And we were skeptical of that at the time. In fact, we had a very fun robot project going at IBM. By then, I had become the manager of it. We put together a robot songbook, and one of the songs dealt with this. The lyrics went something like, he don't put dips in, he don't wrap wire, so them that wraps it cannot retire. But old man robot, he just keeps rolling along. But the reality is that all the people who put dips in or wrapped wire, they better have retired by now. Now, an awful lot of people who think that robots are going to have vast influence in factories have never been in factories. And if you're one of those people, I would urge you to go see some real factories. Because in real factories, what you find a lot of is hard automation of things called transfer machines. So here's the Renault steering mechanism in 1980, which had about 30 parts to it. And this room-sized machine can bang them out at about 1 per second. Of course, a machine like that in 1980 would have cost at least $1 million, maybe a couple of $1 million. And all you had to do was make one minor change, like you want this to be slightly bigger or out of a different material. All of a sudden, the machine wouldn't work. So it's not programmable in any sense. And programmability is a great virtue in factory machines. But programmability does not necessarily mean robotics. Getting back to history, ancient history. Here's a wonderful machine from 150 BC approximately. It's an automatic doorman. The idea is you build a fire at A, that heats up the compartment B, and as a result reduces the air pressure here, so the water from D moves over the siphon C, D becomes lighter, and through these pulleys and a counterweight F, the capstans rotate and the doors open. And then when the fire goes out, the doors close. I don't know if it was ever built. Another example from history, the famous Jacquard loom, which was the first use of punched cards to do anything really useful. The idea is that you have a stream of punched cards here, and the punched cards determine which threads are raised and which threads are lowered as the shuttle passes back and forth for each pass. Punch cards then became important in the subsequent years. A group calling themselves the Luddites were quite unhappy with machines of this type. And so for years they went around smashing machines until in, I think it was Nottingham, the British Army rounded up 50 Luddites and executed them, and then that sort of did away with that movement for a while. There's a lot of Luddites still around today, though, I think, neo-Luddites. Then along came Charles Babbage, first with the differential engine and later with the analytical engine. And somebody realized the analytical engine needed a programming system, and that was, the first programmer was Ada Lovelace. Ada Lovelace is the only daughter of Lord Byron, which ties together with the fact that as a child she would have been growing up knowing Mary Shelley and would have been quite interested in the general topics of automating what humans do. And finally, of course, Herman Hollerith saw an opportunity to build a census tabulator in 1890 using punched cards, and he founded a company which later merged with 3 others to become IBM. Nowadays, it's impossible to find a automobile factory, with the sole exception, I believe, of Lamborghini, where robots are used. The original Unimate robot was invented by George Duval, but he didn't have an opportunity to actually market it, develop and market it, because he worked for AMF at the time, American Machine and Foundry, which had invented the pin setter, automatic pin setter for bowling alleys. And AMF looked at everything and said, it's not another automatic pin setter, we're not interested. It didn't matter what it was. So they weren't interested, but along came Joe Engelberger, he was interested. So he formed a company and George Duval joined it. They came out with this machine called Unimate. And then they found that American car factories didn't want them. So they moved to Japan, and they had no difficulty convincing people to use it. And Japan used them all over. But as I say, nowadays, any factory, car factory you go to visit has widespread use of robots. Here's a really wonderful robot from relatively recent years. This is one of Amazon's factories, but this is Kiva Systems, so you can look them up on the web if you want to. Imagine a factory in which there are a warehouse in which there are lots of things stored on devices that look like this, that have empty space underneath. Huge factory the size of 3 football fields or more. And now a request has come in that's a specific package has to be sent out to somebody, and it has to have one of these, and one of these. These robots go scurrying all over the factory. They know where to go. The mechanism on top then screws up to lift the tower, and then it brings it slowly down a narrow aisle, moves to a rapid street, and goes zipping down the rapid street and delivers these towers with a laser pointing to the specific bin that the operator should take something from. And an operator then takes things, and here's your first thing, it moves on, here's your second thing, and then during their spare time, these get recharged at a recharge station. There are good movies of this on the web. I recommend you see them. What about medical applications? Well, here's a research effort. Penelope Scrub Nurse in the year 2005. I worked on a project demonstrating feasibility of RoboDoc, getting robots to precisely grind out the inside of a femur to accept a cementless hip implant. Subsequently, a company was started up with venture funding, and one of the people in my project joined it, became the head of that project, but they had difficulty getting FDA approval, and it took years, and in the meantime, a German company got more rapid approval. So that didn't work out. Minimally invasive surgery is an application area for robots. The first concept of minimally invasive surgery dates back to 1800, but it wasn't until a laparoscope was invented around 1910 that there was some progress made. Around 1987, if you looked in an operating room, you could see a scene like this where a surgeon was holding the business end of a tool. The patient is lying on the table. He's been inflated. And one of the tools is a camera, so he can see what he's doing. And sort of because of the fact that the midpoint of the tool is not moving, he's moving in a mirror image of the actual motions. And then you advance just a few years to the year 2000, and the surgeon has moved. He's now sitting at a computer station looking at a display, and he's controlling robots which are manipulating the tools. In the future, you can expect minimally invasive surgery in a magnetic field so that MRI can be done at the same time that surgery is being done. Of course, the robots will have to be made out of plastic, because the magnetic fields are so enormous. You can also expect in the future minimally invasive surgery using intestinal crawlers, such as this one, which can clamp on and do something. And then in the distant future, using nanorobots. But I want to be very precise here. You can expect this. I don't believe that's ever going to happen. Now here's a wonderful medical application. This is SIM-1, built by Aerojet General in 1975. You see it here at UCLA, and it's being used to teach medical students how to perform tracheotomy operations. It has a pulse and respiration, and they're performing a tracheotomy operation on it, and if they do it wrong, it dies. That's SIM-1. SIM-2 automatically sues for malpractice. The more modern version of this is Hal. He's just fainted because his girlfriend had a baby. And here you can see his girlfriend and the baby also. Gomard built these devices. Rehabilitative robots were pioneered by the Rancho Los Amigos Hospital in Downey, California, but a lot of work has been done also at the Palo Alto VA Hospital. Here's a scene in 1989 when you have a quadriplegic, and the challenge is to get the robot so that it can do some feeding operations, present drinks or food in a form without stabbing him with a fork. Here you see a physical trainer intended for teaching somebody how to walk after they've had a stroke and they now having difficulty walking, so they get strapped in and they're guided through the motions. The idea is eventually they learn the proper motions. Although I think there would be a bigger market for doing the same thing with a golf swing. Nobody has tried that yet. Here's the Lear Sigler mail mobile in 1980 following a chemical line on the floor as it delivers mail. More practical, more significant service application is hospital delivery for Meals Linen and providing a teledoctor who can have a discussion with a patient even though the doctor is far away and doesn't have time to commute in Los Angeles traffic. Recently I've seen some speculation that with Ebola or possibly other diseases that it would be possible to try to develop robots that could deal with that so that people wouldn't have to be in the dangerous environment. But I'm a little skeptical that that would be feasible because the operations that need to be done are very dexterous operations. Now the topic of military robots. Wonderful example from history is this walking tank that can leap across a boulder-strewn field rather than navigating around the boulders, therefore presenting less of a target, although if you shot out some of the hoses, it would have to limp. And here's one of the drones that I think was deployed during the Iraq War. The DARPA Grand Challenge in 2005 was to get a vehicle to drive about 200 miles across the desert. The winner, of course, was Stanford. And then the following year, the challenge was to drive in a sort of simulated urban environment. The winner this time was CMU. Stanford came in second. And there are clearly non-military implications of this. I mean, all of us have probably seen the Google self-driving car driving down the road. And it's really come a long way since 23 miles per year, because it now goes about, 55, 60 miles, 65 miles an hour. I wonder what the ethics, though, is, because when I drive down the freeway, typically everybody goes at least 5 miles over the speed limit. Now, would a robot car, does anybody here from Google, would a robot car stick to the speed limit, or would you have the option of overriding it? And then if it had an accident, who would be considered at fault? Because you've overridden, and can it get a ticket if it's for speeding?
I talked to Mike. I invited Mike over to NASA and he spoke. And it attempts to do relative, if the crowd is going 5 miles an hour over the speed limit, the car will do 5 miles over the speed limit.
But then it's speeding.
It does relative motion. But you could, but California law is such that you can also be ticketed for going too slow, as a friend of mine
Yes.
in biology was.
Yeah, but not going the speed limit. You can't be picking.
Well, it's called the basic speed law, as you're.
No, well, yeah.
You don't get it.
Then, of course, in movies, we have the Terminator. I'll be back. And we also have this exoskeleton. It was developed by General Electric, called the Hardy-Man in 1968, so that a normal person can pick up a half-ton steel girder. Didn't turn out to be practical in picking up girders, but it did get used by Sigourney Weaver in the second Aliens movie when she had to fight the Queen alien. In the period from 2000 to 2005, there were lots of video programs featuring battles between so-called battle bots, which were all radio-controlled vehicles with all kinds of terrible weapons. It wasn't until Isaac Asimov came along that one had the idea that robots would be benevolent. He invented the 3 laws of robotics. First, that robots may not injure people, then they must obey orders, and finally, they must protect their own existence. There's a whole series of short stories that he wrote then based on the ethics of conflicts between these different laws. And then there's a final story in which he creates a machine called Megavac, which is, of course, 1 million vacuum tubes, but that was a long time ago. It's been given the challenge, is there a way of reversing the second law of thermodynamics? And Megavac computes for more than 1 billion years, and finally it figures out the answer, looks around to tell somebody the answer, and there is no sentient life left on Earth. So Megavac feels rather frustrated by that, and Megavac decides he's going to try it. So Megavac says, let there be light, and the universe starts over again. Household robots. You know, here's a wonderful example. This is from the World's Fair in New York. This was demonstrated. This is the Westinghouse Televox robot. It's got a very primitive speech recognition system here so that he can yell into the microphone on, and as a result, this vacuum cleaner turns on, and it gets this spot on the floor, very, very clean. And progress in the next few years was having similar machines, but you could sit on your couch with a joystick and guide it around, which really doesn't do very much. So it isn't until Roomba comes along for my robot that you actually have a vacuum cleaner that is useful. And last time I looked for the census of robots in the United States, I discovered that there's more than 2 million robots already installed in the United States. But it turns out that at least 2 million of them are Roombas. So you have to, if you hear the statistics on this vast number of robots installed in the United States, you have to be rather careful about what they are. There's also a version that does lawn mowing, and there work some competitors that you don't really see very much of. There's lots of educational robots. I thought that was telling me I should stop soon. I actually once had my phone go off during a rehearsal of the San Francisco Symphony. Anyway, education robots, and you see some of them around here. Robotics is very, very useful for education because it's cross-disciplinary. Electrical engineering, mechanical engineering, computer engineering, and industrial engineering. And there's a whole range of robot toys, old ones and new ones, and robot pets, some of them shown here. And then strange robot pets or animals, like Mark Kutkowski's Sticky Bot or dinosaur here. And speaking of dinosaurs, let's get to entertainment robots. There are lots of robot dinosaurs starting around 2004. Robot fish starting around 2004. And demonstrations in an environment like this, where somebody would put on a show with a radio-controlled robot. August Huber, Swiss inventor in 1939 with this robot Sabor 4, or something rather similar built by Westinghouse and demonstrated in the World's Fair in 1939. Electro, here's Sparko the dog. Sparko had a heat-sensitive nose, so it would sidle up to people's legs. No truth to the rumor that somebody left the back door open and a car drove past and he took out in pursuit of the car and got run over. That's not true. Anyway, he had about 20 different skills, one of which was smoking cigarettes, and that might explain why you can't see him today. Here's the 26th degree of freedom walker by Honda called Asimo. I've seen this in show here at Stanford about 4 years ago. And you know, there's a scene in Wizard of Oz where the wizard is yelling, "Pay no attention to the man behind the curtain." But in fact, I look at this and I watch it, and there had to be a man behind the curtain. Here's the origin of walking robots is Wobot by Ichiro Kato in 1973 at Waseda University. Then subsequently, several people tried to make robots that were faster and much more efficient. And because this could only move very, very slowly and painfully. But here's a relatively newcomer, the Cheetah, built by Boston Dynamics, and last year reported a speed of 29 miles per hour. The hope is that it can carry munitions while soldiers are going into battle. Then there are whole lots of companies throughout the Far East, particularly, that have built humanoid-type robots that do not do anything useful. And then there are so-called robot musicians who simulate playing music, but don't really do it, although this one really does play the drum. These are not really playing trumpets. Then a more recent challenge has been, how do you do robot cooperation? And here's an example in 2006 with robots that learn to cooperate to compete in a miniature soccer game. And actually, earlier this year, I think it was around March, a life-size soccer game, a robot actually scored a goal against an inept human goalie. But it's kind of startling that that could be achieved. Here are robot dancers, and that brings me to the topic of female robots. That theme originated in the Tales of Hoffmann with a story called The Sandman, which was the inspiration for the ballet Coppelia by Delibes in 1870, in which the toy maker is so drunk that he doesn't realize he thinks this is a toy that he built. In fact, it's a teenage girl who's broken into his toy shop and is pretending to be a toy. The movie Metropolis by Fritz Lang in 1927 featured a robot in the image of the heroine Maria. And it's the mad scientist Rotwant has created this robot with the intent of having the robot instigate a class war that should destroy everybody. So she's not that nice. You see the same theme of female robots in other examples recently. More recently, 1972, the Stepford Wives, in which the men of Stepford, Connecticut, led by a former Disneyland technician, are slowly exterminating their wives and replacing them with robots who are absolutely indistinguishable from their wives in every respect, except that they never get headaches. And there's also the inverse theme being a male robot with a human female. And that's exemplified in the movie Demon Seed with Julie Christie, where the robot takes advantage of her. And I'm told that in the entire history of computing, that is the only documented example of a robot failure that can't possibly be blamed on software. So as I say, with a larger audience, more people laugh. Puppets. This is a highly automated puppet. Seems very real. It's really a robot. And there are more modern versions of that intended for deployment ultimately in information booths, possibly in large department stores where you can go and ask, where will I find such, and the machine will tell you and you'll think you're dealing with a human. Then we come to movies. Here's so many examples of movies. I'm only going to use a few. Bela Lugosi in The Phantom Creeps, handsome fellow on the left. Mysterious Dr. Satan, where Copperhead fights the robot. Here's Gort, Patricia Neal, and Michael Rennie in The Day the Earth Stood Still. Here's a really good one. It's Robbie the Robot in the movie Forbidden Planet by MGM, a very successful movie, especially considering how old it was, 1956. But then again, they had an advantage. The screenplay is an iteration on an earlier screenplay, and the earliest screenplay was written by William Shakespeare, and it's called The Tempest. There's Yul Brynner in Westworld, a robot gunslinger gone crazy. Here's Peter Weller as a half-robot in RoboCop. And then, of course, we have Star Wars. And then the movie 2001: A Space Odyssey. This camera here is all that constitutes the robot. It's just a vision system, but it's Mission Commander Poole and Bowman have gotten into the pod here to discuss Hal's malfunction without being overheard, but he's reading their lips and he's not happy at all. And graphics animation makes it seem as if robots are real, even when they're not. Finally, there's hazardous environments. Here you see robot submarine arms in 1980, so that the robot can harvest coral to be sold to tourists. And robot underwater vehicles, which you see here. And of course, robot vehicles were very important for analyzing the Titanic. In terms of flying, people have tried for a long time to build robots that would fly, but the first example of it is 1984. McCready built a robot pterosaur that could actually fly, and there are cheap versions of this that are available. Of course, a modern version is the military version called Predator. Well, there are more modern versions of that, but drones. And then these things are shrinking, and of course you can buy quadrotors at many places today, which can carry a camera, and those can be considered to be drones. NASA has a shuttle arm in 1981, and then the International Space Station got an arm in 1999. And NASA has also designed a robot back in 2005. Then there are robot vehicles that have gone to other celestial bodies. The pictures taken here obviously were not on other celestial bodies. And a really hazardous environment is the inside of a volcano. So here's one that was built at CMU.
Yeah, but that one didn't walk more than 20 feet.
Yeah, it fell in, I think, or something.
No, the fiber optic cable broke.
Oh,
We
was that
discussed that at the USGS last week,
Okay.
actually.
And then putting out fires may seem like a silly application, except that last year, I think 17 firefighters were killed. I forget it was New Mexico or Arizona, so it's not such a silly application. But here, when we come to the toilet application, the original image would have been, can you make a robot that would go in with a scrub mop and clean out the toilet? And so that's not the way you do this. You redesign the whole toilet experience. In the same way, back a long time ago, McCarthy and Minsky said that they would like to get a robot and program it to put together a Heath kit with 1,000 parts to build a television set. A television set doesn't have 1,000 parts anymore. Heath kit is out of business. You don't build television sets that way. You redesign for automation. You redesign for ease of assembly. Now I'm going to speculate in the last few minutes of this talk on the future of robotics, but I got to tell you, speculation is dangerous. As Yogi Berra, the former Yankee catcher, said, prediction is very difficult, especially about the future, except that Yogi Berra didn't invent that quote. Niels Bohr said it long before Yogi Berra said it, except that Niels Bohr didn't invent it because Robert Storm Peterson said it, and before him, Mark Twain said it. And I don't know how to go any further back than that. So I'll give you my summary and conclusions. Kiplinger, January last year, said the United States is on the cusp of an explosion in robotics that will have a significant impact on business and the economy over the next decade. And Time magazine had this cover, you may remember it or not, The Robot Revolution, showing a robot putting together things. It's a rather impressive prediction. But wait a minute. When was that cover published? That cover was published more than 33 years ago, predicting that the robot revolution was here. And somehow or other, the robot revolution hasn't appeared yet. So let's talk about another prediction. Over 60 years ago in 1952, somebody made this prediction: a trainable robot will comprise hands, sensory organs, a memory, and a brain. The largest industry ever to exist may well be built upon its development. The progress achieved by industry in the next 2 or 3 decades, that's by 1982, will be the substitution of machines for men in production. Trainable robots will perform the manual operations of human operators and be readily modified to perform any one of a wide variety of operations. Well, that certainly didn't happen in 1982, so you may all be wondering, who is the idiot who made this prediction? And the answer is, it was William Shockley, and he's no idiot. He's co-inventor of the transistor, he's a Nobel Prize winner, a member of the National Academy of Sciences, and he was a Stanford professor. And the point is that very smart people can make predictions and be wrong about them. I consider myself pretty smart, and I'm making a sort of a negative prediction, and I may be wrong. We'll see. Here's some sober appraisals from 1973. Back in England, when Donald Michie was building this huge robot to put the car together, it took 8 hours, the National Research Council commissioned Sir James Lighthill to evaluate the work on robotics research. And he looked at it, and he said that they're building towers, they're doing puzzles. The stimulus is the urge to compensate for lack of the female capability of giving birth to children. That is not exactly a very flattering report on the state of robotics research. I heard Joe Engelberger make this statement in 1973 at a robot conference. He said, "I see a crop of starry-eyed graduate students." Are there any starry-eyed graduate students here in the audience? "Trying to build intelligent humanoid robots. They get their PhDs, but in the process they realize it's impossibly difficult. So they move on to other areas, and a new crop of starry-eyed graduate students takes their place." That was his assessment. But the popular press said that a robot revolution was imminent. So I would caution you to beware of exaggeration. There are several reasons why exaggeration occurs. The first one is people like to exaggerate, but it's also the Genesis effect, as I would term it, which is that the Bible says that God created man in his own image. And so the Genesis effect is that man wants to create robots in man's image because we want to be God. The second is vast improvements in computer graphics. They make the robots look so real that you think they must be real. It's like in the Mikado at the end. He's trying to justify why Nanki Poo wasn't executed. He said, well, it's like this. When the Mikado says, let a thing be done, Mikado's word is law. So it's as good as done. And if it's as good as done, why not say so? Then academic researchers are competing for grants, and salesmanship wins over science. You don't go for an NSF grant saying, well, I'm not sure if this will work. It might not. You say, of course it's going to work. You know, we've got the best team in the entire world, and we're going to advance the technology, and it's going to do wondrous things. And the same sort of exaggeration occurs, salesmanship versus science, in startups' competition for venture funding. And finally, the press is always eager to publish things, and the press has no memory at all. So the press doesn't know what was done 30 years ago. But I remember John McCarthy talking about this very briefly. I had a conversation with him in 1977, and he said, what I thought would be accomplished in 1 year has actually taken more than 25 years. So there's a ratio there. Keep that ratio in mind. What has actually changed over the last 60 years since Shockley made his prediction? Mechanisms are faster, lighter, and cheaper. Computers are faster and cheaper by a factor of more than 1 million. The mechanisms, maybe it's a factor of 3. As a result of this, primarily, you have much more compute power to deal with sensing and feedback, and there are more practical applications of robots, and there's much more money and people in robotics research. But the big factor is what's happened with computers. In my opinion, there's been little progress in understanding intelligence. There's even some argument about what is intelligence. I would define it as solving puzzles and planning and learning from experience. And I'd be happy to discuss that in the Q&A afterwards. But now I'm going to give you my conclusions. The first is that my definition at the beginning, that a robot is anything that's surprisingly animate, is too vague a definition. It encompasses everything, it specifies nothing, and it's not really that useful a definition, because in some sense we already have household robots, lots of them. The second thing is I'm quite optimistic that there'll be lots of good robot applications proliferating as time goes by in all kinds of areas: military security, disaster, search and recovery, space, medical, entertainment, toys, and plant automation. But there is a common theme here. They won't be intelligent humanoids. They won't be intelligent humanoids, and they won't be intelligent humanoids. I'm predicting, there's no point in my predicting there won't be any intelligent humanoids in my lifetime because I'm pretty old. But I'm predicting there won't be any intelligent humanoids in your lifetimes, and I see some people here who are very young, and I'm predicting that. Who knows? There are major difficulties ahead. Motion dexterity. Humans have more than 100 degrees of freedom. Robots rarely come anywhere close to that. Vision recognition is an amazingly difficult task. A lot of progress is being made, but still the machines cannot compete with humans. Natural language understanding. When I give this talk to a completely lay audience, they occasionally come up with a comment, but I have a machine, Siri is on my machine, it understands me. It doesn't understand you, it's speech recognition. It can recognize speech and it can do a few keyword search, but it certainly could not listen to this lecture and then intelligently answer questions about it. Additionally, when people speak, very often they speak with very poor grammar. And this completely confounds the linguistic approach to natural language understanding, which depends on reasonably good grammar. And finally, the real world is a three-dimensional world, which means we move around in 6 dimensions at the very least. There's X, Y, Z, roll, pitch, yaw. And these motions are very, very complicated. And if you think that it's easy, then forget about programming languages. I challenge you to write a manual in your native language, like English, on how to tie shoelaces. And then you begin to realize, oh yeah, this is pretty hard. And then learning by experience, and learning quickly by experience. Very, very difficult to generalize from examples. Final chart. The social implications of robots, in my opinion, are going to be very minor compared to the social implications of computers, which are enormous. So I'll take you through all of history. It started in the Stone Age. We progressed to the Copper Age, then to the Bronze Age, and then to the Iron Age. And then iron was used to get us into the Industrial Age, when we see scenes like this, Charlie Chaplin in Modern Times. And then we progressed to the Nuclear Age, the Atomic Age. When I was a kid, I was told, oh yeah, everything's going to be run by nuclear power. And somehow that view didn't last very long. And then in '57, with the launch of Sputnik, we were told, oh, we're living in the space age and it's going to revolutionize everything. And then we were told, well, wait a minute, no, the understanding of the genetic code is going to change everything. We'll be able to build things out of artificial protoplasm and so forth. We're living in the biomed age. The reality is we're living in the information age. And our kids are probably living in the information age also for some time to come. So I've given a talk that deals with the fantasy versus the reality of robotics and the future. And my conclusion is that much has been written, and of everything that's been written, a little is actually true. I invite people to contact me afterwards. I'm taking the dangerous step of putting my email up there. So that's the end of the talk, and I'll deal with questions now if there are any. Les.
You neglected to mention some of the attributes of William Shockley's perception of intelligence. He organized a course here at Stanford to prove the inferiority of blacks compared with whites. And that says something about his intelligence.
Surely there must be questions here. Yes.
You were saying that robots cannot understand speech, but what about IBM Watson? It seems like it's pretty good at answering questions that I cannot answer. Even when the answer is told, I still don't understand.
Let me say something about the history of IBM Watson. My last year at IBM was 1994. I was in charge of the AI department, and there was a natural language project there. And I killed that project. So the project then, after I left, eventually came back to life and created Watson. So obviously I was wrong in killing it, although there's a whole story behind that. But yeah, Watson, I don't know much about it. I mean, I'm not privy to how it was put together, but it looks to me like a huge statistical system with an absolutely enormous database, and it's doing some statistical analysis of things. But when we talk about natural language, the tasks that a system like that cannot cope with are very different. That's still a highly structured task. And in highly structured tasks, I think, yes, that kind of analysis has been successful and will be successful in the future. But that's very different from being able to have, for example, a robot servant in your house and tell it, I think I want it. Nah, yeah, I guess I do want some soda. And it knows that you mean root beer and that you don't mean some other drink or whatever. And it knows that you mean you want it cold, and it means you want it now, and you means you want it on the table. I mean, there are a lot of inferences in there. It's very difficult, particularly if you're indecisive and you're not speaking clearly and you're using ungrammatical phrases and so forth. The questions are always expressed very, very clearly on Jeopardy. And so Watson didn't have difficulty understanding what the question was. They were fed in already in automated form. In general, speech recognition is taking speech and turning it into text. And I'm saying that the difficult problem is understanding what the text really means. Anyhow.
As someone who was closely involved in AI and robotics at IBM, IBM did early research in AI and robotics in the 50s and 60s, but then I heard that it didn't commit in a major way because at a brand and marketing level, it was very concerned as a company as being perceived as displacing human labor, and that actually affected its commitment. What did it look like from the inside?
I joined IBM in 1970, and our robot project began in 1972. And for many years, we were told that we should not use the term robot, we should use the term mechanical assembler. And when I took over the project finally, I forget when that was, must have been about 78 or something like that, 79. The first thing I did was get that rule changed so we could use the word robot instead. I never heard that concern directly. I did meet with some members of the press from Germany, and I don't remember what year it was. And I was told before the meeting by our communications experts, be careful what you say because people in Germany are very concerned about the loss of jobs that automation will mean. So don't say anything that would imply that. And so I was very, very careful. And then the articles came out, and the article said that I predicted that robots would take over all the jobs in Germany. So anyhow.
A robot wrote that.
Sorry, you've been very dismissive about the level of intelligence of robots. And we read in the articles in the papers saying that the intelligence is raised to the level of an insect, or perhaps a cockroach.
I've noticed that insects are able to self-replicate. I have not yet seen a robot that's smart enough to self-replicate. No, when it comes to doing puzzles, in general, the puzzles by which we measure intelligence, the puzzles have one answer. and we say, okay, how rapidly can a human being get that answer? That's a measure of his intelligence. But speed may not be a very important thing. I mean, it happens that humans live a lifetime that's on the order of 80 years or something like that, and so that determines our scale of interest. But you can imagine that maybe on some other planet there are creatures that live 1,000 years, and they would consider somebody smart who solves that problem in 3 minutes, but who solves that problem in 100 years. I don't know. If you look at it from the point of view of society, it's taken hundreds of years to solve the four-color map problem. It's taken hundreds of years to solve Fermat's last theorem. And does that mean that as a species we're not intelligent? I don't think speed is as important as people generally consider it in IQ testing. But it's easy to make up a problem and saying, okay, let's design a computer that can solve this sort of problem very, very fast. What's really hard is to say, okay, I've got a computer that can solve any problem. Now I'll give it a problem. So I'll give you some problems. I would claim that computers would have a hard time with this problem. Here's a field with 4 fences and 2 lakes. And your challenge is to draw where the fence would go that would go to that point and that point, but you're only allowed to use a straight edge. That's a hard problem. That's the kind of problem, I'm sure you could design a computer that can solve that problem, but I'm sure there isn't any computer that can solve that problem today. I don't know, did I answer your question or did I leave it open?
I think you left it open enough for
Back row.
iRobot's Baxter, the thing Rob Brooks has come up with. How smart is that thing, really? I've seen all this vague stuff about it, but I don't really see what it's capable of learning yet.
You know, I don't know either. I looked it up, I don't know, a couple of months ago because the assertion appeared in the newspaper that it was a very intelligent robot and it could learn or something like that. And then I looked at the website and I couldn't glean any more information from it. So I don't know exactly what it can do.
Its advances in compliance. It can work safely around humans.
Okay.
And it's relatively programmable.
Compliance is really an important topic. And I mean, a human can pound on a table without hurting the table or the human hand. In general, robots up to now cannot do that. And maybe that's the sort of thing where the skill has been developed. But I don't know. Sorry, I don't know the answer.
I always had this thought about my robot challenge would be, you know, like how 2 people are walking down the sidewalk and they don't like talk about it and they don't even really make a lot of body language. Maybe they only see each other for a split second, but they don't walk into each other. And then I thought, so that's always my challenge. And I thought, then this may be a prototypical female thing because I'm thinking about more than just the robot, but the robot inside some environment.
I don't know, is there a question?
Well, the question is, why isn't that the level of intelligence inside an environment rather than singular?
Let me give a tangential reply and then I can see that my time's run out, so it's going to be the last question. If you watch the movie Matrix, there's a scene where Morpheus and Neo are walking through a crowd. And as Morpheus walks, the crowd just parts around him. And as Neo walks, he bumps into everybody because he hasn't yet learned how to control the environment. I don't know the answer. I guess, yes, it takes some skill to avoid. You don't want to bump into people because in some cases you bump into somebody they
I
may...
guess it also boils down to, if it were 2 robots, would they be able to do that kind of negotiation and communication?
I think that would be fairly easy to do. You put in a random number generator and tell each one to go in a random direction after a random time. And if they both go, well, there was a Mutt and Jeff cartoon where they invented a spring under the car so that you would avoid head-on collisions. Unfortunately, the other guy invented it too, so they still had a head-on collision. But I think that there are easy ways of avoiding that kind of a collision.